Next is a brief discussion on some of random variables which are not random, which are not normal random variables. So some of random variables. So we know that if it is a normal random variable and they are IID, then the sum is another random variable, normal random variable. So IID normal variables, their sum is another normal random variable, and their sigma can also be summed. But is it only true for normal distribution? Now let's see if we have binomial distribution. So binomial distribution is x1, which has a parameters of m1p, which is m1 tosses, m1 tosses of a coin, and we are counting the number of heads, and the other one is, and we have a bunch of these. So we have an x2 which has a parameter of m2p, and xn which has a parameter of mnp. So each of these are adding. So now in total what you really have is an m1 plus m2 plus mn number of tosses, and x1 plus x2 plus xn number of heads, and p is the same. So effectively we have tossed the coins that many number of times and obtained that many number of coins of heads. So for binomial distribution also, as long as the p is the same, you can just add the variable x1 can be just added. So y, the new variable y, can, of which is x1 plus x2 plus xn, has binomial distribution with parameters of m1 plus m2 mn and probability of p. So that is true for binomial distribution. And if we look at the Poisson distribution, suppose xn is a Poisson distribution with a parameter of lambda 1, x2 has a lambda 2, and xn has a parameter of lambda n, then the sum y is equal to xn plus x2 xn will also be Poisson with a parameter of lambda 1 plus lambda 2 plus lambda n. And if the sum has an expectation of a Poisson distribution is lambda, so expectation of y is going to be expectation of x1 plus expectation of x2 expectation of xn, which just means lambda 1 plus lambda 2 lambda n. As long as everything else, the distribution remains the same, then you can just add them. And this is true for binomial and Poisson distribution.